All right, welcome everyone to the GeoQuEST seminar. As always, I would like to start by acknowledging the traditional custodians of the lands on which the UOW is situated. We pay our respect to the Aboriginal elders past and present, who are the knowledge holders and teachers. We acknowledge their continued spiritual and cultural connection to country. As we share knowledge, teaching, learning, and research within this university, we also pay respect to the knowledge embedded forever within the Aboriginal custodianship of country. Today, our speaker is Colin Woodroffe. He's a professor here at UOW. He has written a book on coastal landscapes, and his research focused primarily on coastal landscapes in Australia, New Zealand, Indies, and a few other places. I will pass it on now to Colin, who wishes to speak a few words before we start. Colin,
thank you, Sean. Thank you very much. The talk I'm just about to give is a keynote presentation that I gave at the Core 21 conference in China a few days ago. And it occurred to me that it would be useful to share this with my colleagues in SEALS and GeoQuEST and also my coastal colleagues, as there's several topics here that we've been having some preliminary discussions about. It also provides some background on my perspective that we will bring to an ARC Discovery grant that Kerry Lee Rogers and Sarah Hamilton are leading with myself and others, and with several students about to start on that. So I hope that this is useful background for you all and what I do. And with that, I'll start. This is pre-recorded, and I hope everything goes okay if I start the presentation.
Yes, so since this talk is pre-recorded, we will once again be leaving all the questions till after the talk. Okay, go ahead and start now.
Thank you for this opportunity to present a biogeomorphological perspective on the response of coasts to sea level rise. Let me give an outline of the talk. In this presentation, I'd like to start with the words that are attributed to Charles Lyell. The present is the key to the past. And that, of course, was the way in which geologists came to understand the past by realizing that present processes had also operated in the past. I'd like to rephrase that in terms of our perspective that the past is a guide to the future, and that we can understand different timescales that, for instance, geological over thousands of years, that we can think of historical change that we might be able to have observed, that there are events that shape the morphology of our landforms, and of course that they are operating in response to processes that are such as waves and tides. This sort of perspective might allow us to consider how coasts might change in the future. Whereas I've described this in the past, the perspective I'd like to take today is that the past has left a legacy and that the future is partially dependent on that legacy from the past. Well, I'd like to start with a little about my past. As an undergraduate at Cambridge, I was greatly inspired by Professor David Stoddart. And as a consequence, I went on to undertake my PhD under his supervision. And in that PhD, I was studying how the mangrove forests in the Cayman Islands had developed. The green on this map are the extensive mangrove swamps that occurred naturally on Grand Cayman before many of them were cleared. These mangroves, quite extensive, and a younger version of me, coring through various sections of the mangrove, and here is the sort of peat, the very fibrous peat, particularly underneath Rhizophora, made of root material. And what my transects and coring indicated was that mangrove peats extended below the intertidal range in which mangroves presently grow, and radiocarbon dated, indicating that these had formed in the past and that as the sea had risen, so these mangroves had extended inland. So I took a biogeomorphological perspective from an early stage in my first paper, as it happened, compared mangrove distribution and coral reefs, indicating how there was a legacy that reefs in the past had influenced the distribution and the morphology and shape of mangroves in present. Later, as I was on the steering committee of the Land-Ocean Interactions in the Coastal Zone core project of the International Geosphere Biosphere Programme, I had a particular responsibility for Focus 2, which at that time was called Coastal Biogeomorphology and Global Change. I was not central to shaping this. I had inherited this from somebody else, but it's very instructive, the structure of that project. We could envisage antecedent biogeomorphology that had an influence on the existing biogeomorphology that was going to influence, as global change took place, future biogeomorphology, recognizing the natural environment and its variability, and of course the important impacts of people. Well, coral reefs have been central to our understanding of past sea level change, and this diagram synthesizes our understanding of the last 500,000 years of sea level variability and the numerous dates on coral, initially some radiocarbon dates, but primarily uranium series dates that indicate coral reefs provide some perspective on past shorelines. And particularly prominent, of course, are those on the Huon Peninsula that John Chappell described. But those reefs occur extensively, and here we are in the Cook Islands examining some of those. Well, that was the Pleistocene. As we move from the last glacial maximum, so dates from particularly corals, but also mangroves, have influenced our understanding of that rise of sea level, the post-glacial rise of sea level from the last glacial maximum about 20,000 years ago up to around 5,000 or 6,000 years before present. And that comes from coring under many submerged reefs. Our work here on Lord Howe is only a small example and hasn't contributed to this much greater understanding from places like Barbados, Tahiti, and John Chappell's work in the Huon Peninsula. But in the in those last few thousand years, Holocene, the mid and late Holocene, corals have provided evidence of the sea having been higher in some places. Here we see living microatolls, as we do again here, and some fossil Holocene reef, and here again some fossil microatolls. So these organisms, these corals growing here that preserve in this, form part of the geomorphology, are an interesting case of a situation where we're going to see that there is a past morphology preserved as a result of these sea level changes. Holocene sea level has been the subject of much study. The initial study came largely from Europe and North America, and there were a series of sea level curves until Rhodes Fairbridge from Australia began to point out the variability when he put all dates together. And this was finally resolved when it was begun to realise that sea level had done different things in different parts of the world. And this is a diagram that has been around for quite some time. We've included it in our book, the book that my colleague Colin Murray-Wallace and I wrote on quaternary sea level changes. And it indicates that the nature of the sea level varies because of the isostatic adjustment of the Earth to the varying loads of glacial ice and water in the ocean. And for our purposes here, we'll contrast the intermediate field at some distance from previous ice sheets with the far field. We'll contrast the West Indies with Australia in particular. This diagram shows the contrast in sea level history for the last 10,000 years for the West Indies compared with the Great Barrier Reef in Australia. The green represents mangroves, radiocarbon dates on past mangrove deposits such as those in the Cayman Islands but also in Florida. And the pink dots here represent coral. Coral, of course, grows beneath the sea, whereas mangroves grow intertidally. So the line for the sea level occurs roughly between those two. On the right here, we see the same records for the Great Barrier Reef. And you see, of course, many more coral dates. Many of these are corals that have grew below the sea level and are not particular indicators of sea level. Mangroves, on the other hand, are found above the sea level curve, but you'll see a series here of microatolls, those corals that have been exposed because of a slight decrease in sea level. We can, in this part of the world, in Australia, sea level reached its present around 7,000 or 6,000 years ago and has been slightly above present and fallen to present more recent years. This diagram shows a schematic representation of coral reef response to a schematic change in sea level. And this comes from, this was presented by Conrad Newman at Coral Reef Congress in Tahiti with this wonderful cartoon. How reefs might either give up, how they could catch up, or how some might keep up. So if sea level rose particularly rapidly, coral reef might be drowned. If it rose again rapidly, the coral reef might backstep with a younger reef forming higher on the substrate. Many reefs on the Great Barrier Reef have had to catch up with sea level. Sea level reached a present level and those reefs lagged behind but caught up. Some reefs, particularly those in the West Indies, were able to keep up. When sea level stabilised, reefs could prograde. They couldn't grow any further vertically. And indeed, when sea level fell, the reef there would be this emergent reef left, this reef flat. Well, in this slide, I'd like to compare how mangroves respond under those two different sea level conditions. Mangroves then in the Caribbean, West Indies, where sea level has gradually risen at a decelerating rate. And the mangroves from the top here, about 4,000 years ago, have been moving landwards, and then they've accumulated that fibrous organic peat in these, particularly on the islands where there's not a lot of terrestrial sediment, on the carbonate islands. This contrasts with the situation in the far field where the sea level rose and reached present around 6,000 years ago and has decreased. Though again, mangroves initially migrated landward, the mangrove ecosystem. Then the sedimentation to seaward enabled mangroves to prograde, to build out again. And so we have this, what we call a transgressive sequence, followed by a regressive sequence. So let us ask whether it is possible then to consider mangrove stratigraphy in a similar way to that presented earlier for coral reefs. Where sea level rose rapidly, mangroves might be drowned. This has been the case on the Sunda Shelf, work that has been done out south of Malaysia. In some cases, they may have backstepped, for instance in Bonaparte Gulf in northern Australia, where again there are mangrove deposits out on the shelf, but there are presently mangroves along the coastline. I'm going to show in a moment situations where the mangrove has caught up. Sea level has risen, and that stratigraphy that I showed on the last slide, where mangroves have kept up with sea level, as for instance in the Cayman Islands, where mangroves have prograded. And there are some situations where the sea level has fallen and there are emergent mangrove deposits. Let me add at this point, and particularly, of course, mangroves have become valued for the important role they play in sequestering blue carbon. That is, their considerable biomass. Their above ground biomass is substantial, but they also sequester lots of carbon below ground. And those below ground stores of organic carbon are a particularly important resource. What my colleague Kerry Lee Rogers showed in this paper in Nature is that as the sea level history has provided greater opportunity for blue carbon accumulation where the sea level has been rising, as for example there in the Cayman Islands, compared with in northern Australia where sea level has been stable for a long time and there has not been as much accommodation space for that accumulation of blue carbon. Well, there are other implications of this difference in sea level story. In Belize, Central America, and in the Caribbean, the Belize Barrier Reef, there are extensive mangrove islands, and here are some of them. And those islands are formed on peat, like as we saw earlier in the Cayman Islands. But this is an area where mangroves are being lost, as shown in this more recent satellite imagery. This is an area that I mapped myself in 1987, and there have been a loss of mangroves in that case. Contrast that with mangroves growing on the Great Barrier Reef on the low wooded islands. And this is work that Sarah Hamilton is undertaking, my colleague at Wollongong, and the mangroves are extending across reefs. And the reason in this case, the contrast, is because, we can see it very clearly in this photograph, there are these fossil microatolls dating from a time when sea level was higher in the past that provide a suitable substrate over which the mangroves can and have been expanding and extending. So that past sea level variability has left a legacy in terms of how mangroves are changing in a general sense in these environments. Let's talk now about the extensive mangroves in the Northern Territory east of Darwin. And there's numerous mangrove species, several tens of mangrove species, but we'll concentrate on three principal ones. And here is the distribution of mangrove species in terms of elevation in the tidal range. They occur above mean sea level and there's a tidal range of some 3 or so meters, a tidal range of 6 meters. The range over which mangroves extend is some 3 meters. In Darwin Harbour, and then along the South Alligator River. And in this case, this is distribution along the river. Here we see some typical zonation of mangroves at the coast. And the sequence is in green, the Soneratia that occurs low, close to sea level, followed by Rhizophora, these very typical mangroves with their prop roots, and to landward Avicennia, shown here in blue. So this sequence represents the elevation in the tidal range from mean sea level to highest astronomical tide, but we can also think of that as representing a succession as those mangroves have built seaward, as they have prograded. Now we know from work that I undertook in the Northern Territory many years ago now, that there has been this pattern of change. 8,000 years ago, as sea level rose, it rose into a series of river valleys. Around 6,000 years, as the sea level stabilized close to present, we had what we've called the big swamp, Holocene big swamp. Extensive mangroves formed. Many of those mangroves have disappeared as the plains have continued to accrete, but there are still extensive mangroves that have built seaward at the mouth of these rivers. And we know that these environments have changed from independent of the rock art that shows the extensive barramundi and these X-ray paintings that coincide with the extensive mangroves in the big swamp, and then the appearance of various freshwater organisms that correspond with the more freshwater wetlands that characterize these areas now. This is a quick summary of the contrast between the coastal plain that has built out in the last 6,000 years and the estuarine plain that has, I'm going to show you in a moment, kept up with sea level. So the 7,000 years ago, as the sea level was rising, mangroves were increasingly expanding landwards. Then as the sea level was stable, along the coast, they have built seawards. And we have the modern situation with this extensive coastal plain. In the case of the estuarine plain, the mangroves were accumulating as they're on a largely muddy substrate, but a very organic substrate from the root material of mangroves. The extensive big swamp persisted about 5,000 years ago, and then those floodplain areas continued to sediment up, and the mangroves disappeared to be replaced by the present freshwater monsoonal sedge grassland vegetation, and the mangroves retreated to just the margins of the river. So these mangroves here on the coastal plain caught up with sea level rise. They didn't keep pace as the sea level rose rapidly, but they have caught up since the accumulation of the subtidal muds out in the Gulf. Whereas in contrast, in the estuarine plain, mangroves kept up with sea level, at least during those the final stages of that post-glacial sea level rise. This diagram shows this in more detail. This is a typical cross-section in the alligator rivers. The green are the mangrove muds. The yellow here are the sediments that are deposited, the sandy muds that occur out in the Gulf. This is a series of, this is the sea level history from about 8,000 years ago as the sea level rose, and these are radiocarbon dates. Our various cores can be shown schematically here. And so in the coastal plain, the mangroves retreated as the sea rose. In the estuarine plain, they were able to accumulate the sediments, partly brought in by the rapid large tidal range, accumulated, and these mangroves persisted until about 5,000 years ago, when they were replaced by the present sedge grasslands. Then over that period, the last few thousand years, the coastal plain has built out successively, and we have some ridges that indicate that. So the estuarine plains have kept up with sea level rise. The coastal plains have caught up. And here I've tried to show schematically the pattern from pollen. We know there's been a succession of changes from Soneratia through Rhizophora to Avicennia. I want for a moment to consider the implications of this for areas beyond Northern Australia. In Southeast Asia, there are large megadeltas at the mouths of many of the large Asian rivers, and these are densely populated with megacities on them. An example here of the low-lying topography of the Red River Delta and the considerable population that occurs on that. Well, these megadeltas have formed in a similar way to the North Australian plains. Here, shown schematically for the Mekong Delta, we know that there is a stratigraphy of, again, mangrove sediments recording that sea level rise, and then subsequent progradation and build out, that transgression followed by regression. This is a schematic illustration of the sea level. Initially, these mangrove sediments shown in the orange here, increasingly extending landward as the sea rose, the marine sediments overlying them, and then the subsequent build out of the delta, recorded in this case by the numerous ridges on that situation. And then we might speculate what's going to happen in the future. These extensive plains, this legacy of the past sea level variation, is going to be subject to ongoing and future sea level rise. And we're going to experience compaction and inundation, redeposition and erosion along the shoreline. I'd like to now come back to Northern Australia and talk about work that I anticipate we'll be able to do in future. This is looking at the satellite imagery available through the Digital Earth Australia coastlines repository that the Geoscience Australia have compiled. And shown in red are areas of erosion over the last 30 years, and in blue, progradation, build out. The progradation is well captured in the example of the alligator rivers that I've spoken about before. Here is one of the areas that seems to be the most rapidly retreating in Australia, Point Stewart. So the shoreline has been retreating at something like 15 metres, up to 15 metres per year on average in this location. While it's eroding, notice, however, that there are ridges in the past here indicating that it has also been variable, the geomorphological behaviour in the past. Let's contrast other areas around the shoreline here, indicating here somewhere where it's building out, and where again there has been an episodic change because the sand has accreted for a while, there are mangroves behind that, and then mangroves have built seaward at initially a rapid and then a more slowly rate, and you can see they're continuing to build here. Here's a situation where the coast is very variable and the rate of retreat has been considerable in some places, but slower where there are mangrove creeks that act almost as mangrove groins. So the pattern of change is very variable around this area here, and clearly there's a geomorphological story that explains some of this past variability and the likely future, ongoing and future response. Just recently, there's been a realization about some of the episodicity associated with events. And this came about particularly as a result of extensive dieback of mangroves that occurred in the Gulf of Carpentaria in 2015. The red areas here are mapped where there have been extensive dieback of mangroves. Work by Norm Duke and others has mapped this in considerable detail. And what their work has begun to show is that this appears to have been related to a sea level anomaly, to a period of low sea level. This occurring in the time when we know that sea level is rising around the world as a result of global change. And this appears to be attributed to an anomaly, southern variation in the Southern Oscillation anomaly. Well, that dieback also occurred in the Alligator Rivers, and with Emma Asbridge and others, we've mapped this. And again, the areas in red show that at the landward, mangroves have been dying back. There's been some mangrove death. This sea level anomaly occurred throughout the region, and it appears to have corresponded with a period of lower sea level recorded in the Darwin tide gauge. So, what can we say about past and then future dynamics? Well, first, mapping that Emma Asbridge has done from, again, before the Digital Earth Australia database was available, but using Landsat, has shown that the West Alligator River here, there have been areas where mangroves have expanded, but other areas where they have been lost. The 2015 event was a particularly marked dieback event, but looking at the ENSO variability, this is the NINO 3.4 ENSO variability, and the Indian Ocean dipole, the coincidence of those things that led to that sea level anomaly would appear to have occurred a number of times in the past. So what can we anticipate in the future? With sea level known to be rising and anticipated to continue to rise, then first of all, we realize that there are these dieback events where an anomalous period of sea level may actually lead to some death of mangroves, landward mangroves that are not inundated but have become desiccated in particularly dry periods. As the sea rises, we might anticipate more extensive mangroves extending back over those plains that were tidal in the past. And what we should envisage is that dynamic of periodic dieback, perhaps in concert with sea level rise. So we do know that there have been considerable variation in the way that mangroves have changed in the past. I go back to some work that I was involved with back in the 1990s, when we mapped the variation of tidal creeks along the Mary River, just adjacent to the Alligator Rivers in northern Australia. And what aerial photographs showed was how a couple of these tidal creeks had expanded over a period of several decades, expanded landward into areas that had not then been tidal. And it led to extensive dieback of the Melaleuca that were growing in those areas in the region. And here we see mangroves extending along those tidal creeks. Here's one of the major tidal creeks and the small tidal creeks with mangroves beginning to establish in the areas where the Melaleuca had died. More subsequently, satellite imagery provides evidence of this expanding mangrove area in these low-lying plains. Now, quite what the trigger in this area was, whether it was a gradual rise in sea level, it didn't seem that it was at that point. But clearly, in this situation, these mangrove expansions have been into past paleochannels. They're re-invading areas that had been part of a former geomorphology. That past geomorphology had left a legacy that was being exploited at that time by tidal creeks. This might provide some indication of the sort of response we might see more extensively in the past as in the future as sea level rises. So let's synthesize what I hope I've been able to say in this presentation. That at the past we can consider a series of different timescales. We've started by looking at the stratigraphy, the geological timescale, and which we could say as the sea rose, mangroves altered their location. They could colonize, they could establish in areas more landward than they had been before, or they could extend seaward. We've talked about historical timescales, such as the capture of those changing tidal creeks in the Mary River from aerial photographs. We talked about an event timescale. We talked about the dieback from this unusual sea level anomaly, but perhaps more characteristic are other dieback events, for instance, cyclone damage that alters the distribution of these communities. What I feel we have not covered very well at this point is the dynamics of particular individual species. We haven't really captured the organismal scale. These mangroves that are establishing along the tidal creek, in contrast to the previous vegetation that has died, these things don't occur instantaneously. That takes time for the species to establish, for propagules to get there. And this is a timescale I think we need to explore in more detail. Let me summarize. I hope in this talk I've been able to demonstrate several things. First, that the past provides insights into the way that systems behave. Secondly, that there is a legacy of the past which predisposes the coast in different ways and at different places in terms of how it will respond in future. Change occurs across these time and space scales, and it is a complex interplay. I think we need to understand the bio in biogeomorphology more than we have been able to at this point. I think there is a lot to be researched in terms of the way that organisms behave. And of course, there is an increasing overprint by human activities. At this point, I've been talking primarily about the natural response of very remote and little changed pristine mangrove ecosystems. But they will be overprinted elsewhere by human activities in the major megadeltas of Asia and elsewhere around the world, and of course increasingly through our alteration of climate, we're having impacts on these systems. Thank you for the opportunity to present these ideas, and I'd like to acknowledge my many collaborators over the many years. Thank you.
All right, thank you for that talk, Colin. Does anyone here have any questions? I think everyone's really quiet.
I have one.
All right, go ahead, Guang.
That's right, Colin. Thank you very much. I don't seem to see a lot of people on the screen. Just a very quick question about the role of sediment supply in the dynamics of the mangrove expansion or retreat. How much actually sediment supply, or in other words, the rate of erosion on the land side plays out in these dynamics?
Yes, thank you, Guang. That's a very good question. And the important thing about mangroves is there are two major supplies of sediment. There's the sediment itself, and there's the organic material that the mangroves produce. And one of the things that really differentiates those great stores of blue carbon in the West Indies, where that is a extremely fibrous mangrove peat, is that there's really very little sediment, and the mangroves are creating their own substrate through their growth and through the roots that particularly form that substrate. In terms of where there is sediment, there are again two sources. Some of these mangroves, like on the Great Barrier Reef and so on, are living on carbonate sediments, and there's interesting questions there about the interaction between relatively acidic mangrove substrates and carbonate sediments that surround them. But if we're in situations of siliciclastic sediments, there again, at least a couple of sources, there's a whole sediment budget question. And in many cases, particularly our North Australian ones, it didn't seem that it was so much the source of sediment coming down those rivers as sediment being remobilized from seaward and pumped into these systems by the tides. So sediment is a very interesting issue in terms of its various sources. We've also got the whole question about the rate of supply and the availability of sediment. One of the curious things is that mangroves do seem to have a capacity, and I'm not sure if Sam's with us here as well, but fascinatingly, we were just talking recently about his work on the Tweed compared with Kerry Lee's work in the Tweed, where he seemed to have extremely organic cores where there was very little sediment being accumulated. So there are certainly these questions about how much sediment is actually available for mangroves to accrete. And of course, you'll be aware of the work that Kerry Lee has been doing over several decades of actually monitoring at particular sites. So I hope that answers that.
Thank you. I think Amy had a question.
Hi, yeah, I really enjoyed and appreciated that talk, Colin. Yeah, awesome. I have tons of questions, but I'll keep it to two and very simple ones. First was with respect to the sea level curves, constructing the Holocene sea level curves, and the idea of using mangroves and coral. Obviously, they record sea level rise better than fall. I've understood from Kerry Lee that the mangroves don't preserve the sea level fall as much. And I'm wondering with corals, do you see a lot of emergent corals? I haven't worked in that area, but as far as trying to capture the fall in sea level, are there many of them?
Yes, there are. Our work, of course, on coral microatolls, that very nice photograph that, thank you, Sarah, which shows very clearly those coral microatolls across I don't think it was Low Isles, I think it was one of your islands in the Howick group. But yes, through across the Pacific, we have good records of sea level variability higher than present sea level, preserved by corals and coral microatolls in particular, which grow up to a point that they cannot grow any higher. And in fact, again, with Helen, we did work looking at the actual sea level record in fields of these microatolls, but also within individual microatolls themselves.
And just the second part of that, if I could. So, and that makes sense because we have sort of a better idea of sea level in Northern Australia. And a lot of times the fall is well defined. The question is more in the mid-Holocene high stand. And I think this is a general question, I don't know, just because I have the opportunity, is that a lot of the two Holocene sea level high stand curves show something that I've seen in the literature a lot, where you see a high stand that extends beyond what is modeled or drawn by the curve. So I think the one for Belize, I think it was, the other far field site, you can see that the actual proxy data extend back 7,000 or 6,000 years, but the curves are drawn much younger. I didn't know if maybe you had thoughts on that, from your Colin's book or your perspective, and then I promise that's my last question.
Yeah, like we shouldn't be distracted by other researchers' sea level curves, particularly that Larkham curve. And in the case of the Great Barrier Reef, as you're very aware, it's still a subject of debate, the details of the sea level curve on the Great Barrier Reef, and variable, of course, across the Great Barrier Reef, not only from landward to seaward, but from north to south. And there are many microatolls preserved, but there is also a danger of microatolls being moated, in which case the coral has been sort of in a little pool that hasn't drained properly, hasn't connected properly with the sea level, which can be misleading, giving you misleadingly high sea level evidence.
Great, thank you.
All right, Jeff has a question.
Yeah, thanks, Colin. That was a Great talk. So the model you had of the mangroves and the way that they respond to sea level rise is largely derived from the macro tidal settings. Just wondering if you can comment on how things would compare in different tidal settings, micro tidal settings. Is it just a muted response or different spatial scales, or is there anything that you suspect will be drastically different?
Yes, a good question, of course. Yes. It's very difficult to pin down in a macro tidal setting the details of sea level differences because the tidal range is so large. And so to try, even though we know something about the mangrove distribution within that upper part of the tidal range, nevertheless, and again, we've got students working on this, Chris may be listening, and some of the work that he's done about tidal amplification along rivers, particularly the alligator rivers. The alligator river, those mangroves reach up to 1 meter higher, or up to, let's call it 60 centimeters higher in the middle of the river, 50 kilometers up the river than they do at the coast, because of the constraint of tidal range up the river itself, the amplification of the tidal range. So there are big questions in those macrotidal systems. Chris is working on that in the microtidal Minamurra, where again we're only talking a few centimeters there. Interestingly, mangroves can grow outside the tidal range too in some situations. So they are not the perfect sea level indicator by any means. I think we still to look for the perfect sea level indicator.
All right, thank you. Phil, you look like you have something to say. Go ahead.
Yeah, thanks, Colin. Love your presentation. Lovely to see your face again. A much bigger perspective question, and I hope it's not sounds too silly, but these glacial minima periods that we're in at the moment, how long do they last for on average? And if we overprint those curves onto where we sit, how long do we have to undergo this current warming trend and sea level rise before we may get into that downswing cycle again? Is that hundreds of years, thousands of years, or tens of thousands of years?
Yeah, it's a great question, Phil. Yes, that cyclicity that we see, driven by what we call the Milankovitch, the orbital parameters, drove, so we best understand it, those fluctuations for the last 500,000 years, with a curious change in that periodicity that going back further. And so, very good question. Of course, on that basis, we can put those orbital things together, as Milankovitch and various other people, Berger and so on, have done, about when we would go into the next ice age. And you'll be disappointed to learn that it's up to something like 50,000 years into the future. But of course, that all works if we don't mess the climate up ourselves. And of course, what we are seeing with global warming is that, and people have actually, I've seen this comment made prior to Glasgow about how the amount of change that we are making to the climate could be as much as the change between a glacial and an interglacial. So we talk about 6 degrees of temperature change between the glacial maximum and the sort of our regular temperature. Well, we've already increased it by one point, and of course, you know, with IPCC going forwards and so on, some of those. So really does look as if those human activities or what is going on with global warming has taken us out of the range of that Milankovitch variability. So I won't have my money on 50,000 years, Phil. I won't be able to pick up the bottle of wine you can give me when the next ice age occurs at 50,000 years, because I don't think it's going to, we've postponed it.
Thank you.
All right, does anyone else have any comments, questions? Nicholas?
Thanks, Colin. I really enjoyed this. I'm just going to go with a bit of a naive one, I suppose. So if I understand correctly, mangroves are pretty good at storing carbon. So in principle, if you take human activity out of the equation, sea level rise, if carbon naturally accumulates in the atmosphere, is it the case that this would give a chance on a low slope for more mangroves to appear and store carbon away, or do you have the wrong picture there? And the follow-up would be, is this possible to happen given human activities?
I'm sorry, Nick, I'm not hearing you at all clearly. Can Sean pass on the question again, or?
I'm so sorry, the microphone was up here. Can you hear me now?
Yes.
Much better.
I'm so sorry, everyone. Let's start again then. If I understand correctly, mangroves are good at storing CO2 away, at least for some period of time while they're active. So is it the case that in a natural system, if you take human activity away, when sea level rises, there's more opportunities for mangroves to grow? As I understand that some will die back, but is it the case that generally sea level rise will give more mangroves? And if the sea level rise is due to natural CO2 accumulation, would that then be a feedback loop there? Do you have that feedback loop right in mind? And then this follow-up question, which is probably very silly, is this likely to be effective given human activity?
Not sure that I've caught all of the question, but they're great questions. I think so. And Kerry Lee and Jeff might be better placed to indicate the evidence for the greater storage of carbon in places where sea level is rising more rapidly. That, of course, occurs in the sediments that are accumulating there. One of the things that immediately comes to my mind is the accommodation space, but not the vertical accommodation space, which that greater sea level rise gives you, but the horizontal accommodation space. So when sea level overtops the Mekong Delta, you've got an enormous spatial area to go back to something like the big swamp that we had 6,000 years ago, and that will trivialize, in a sense, that the horizontal component will be a bigger part of the vertical of the volume overall, I suspect, than the vertical. Now, your question there about human influence, and again, I wasn't quite sure what that would be, but if we go back to the Mekong Delta for a moment, as with all those big deltas, those deltas are subsiding, and they're subsiding probably, and you might know better than I do, in the geophysical sense of why they would be through sediment loading and sediment isostasy and so on. But they seem to be subsiding even more rapidly as a result of groundwater, sometimes hydrocarbon extraction, perhaps some of the land use on top of them as well. So there are these enormous areas where the sea level, which gives a vertical component, would be an important issue. But I think one of the things that we perhaps haven't looked at in anything like enough detail is the horizontal, the enormous areas. And so, it comes back to Guang's question in a sense of, we're all hunky-dory then if there's sediment that can, but once you start trying to keep the whole of the Mekong Delta surface rising vertically at the same rate as sea level rise rate, you haven't got that sort of source of sediment, especially when you've dammed it all up in upstream on the Mekong or whatever it is. So yeah.
Thank you.
Thanks.
All right, Colin, I have a question. So in your talk, you showed a slide where as the mangroves prograde towards the sea, they sort of build up this mangrove substrate over the top of shallow marine sediments. But then underneath that sediment, you have this legacy mangrove substrate. I was wondering, would that kind of stratigraphy be preserved if the sea level continued to rise? And if not, is it then possible that the mangroves have prograded several times in the past and we just don't know about it?
Yeah, that's a very good question, Sean. And I suspect we'll resolve that less in the case of mangroves, which are relatively little studied and inaccessible and so on, than we will in perhaps the marsh deposits of, particularly the salt marsh deposits of the Northern Hemisphere. Those of you who know the the Severn estuary in Britain, or the Wash in the UK, and there are equivalent environments in North America on both west and east coast. There seem to be sequences of peaty layers in between muddy layers, and certainly there are interpretations of all sorts of oscillations of sea level, and of course it gets complicated with that compaction and all sorts of other things that can be going on with the dynamics. But there's certainly, yes, I think that there are areas where there's all sorts of complexity about, but also your question raises a really interesting point about the opportunity to, and this is something that we as coastal folks really need to talk about more, the opportunity to disentangle the transgressive sequence because we look like as sea level rises, we're going back into a transgression. One of the things that I hope was a key point of my point about the legacy is that it's going to be different. So the gradual events that occurred as the sea encroached in onto what is now the Mekong Delta 7,000 years ago differ from the encroachment of a now flat surface. But anyway, I may be getting ahead of your question there, but there's some interesting work to be done, I'm sure, if it can be done, in the stratigraphy of some of those sediments underneath the plains. Yeah.
Thank you. Does anyone else have any more comments or questions? All right, going once. All right, well, we're right on time. It has been an hour since we started, so I will end this session here. Thank you, Colin, again for the seminar.
Thank you.
And yeah, enjoy the rest of the day, everyone.
Thanks.